Okay, in this little mini review, we're going to introduce two more gas laws. Boo. And then also talk a little bit about external respiration. So before we talk about external respiration, let's mention the two laws. And the first one is Dalton's law of partial pressures. So basically, what Dalton's law is saying that the total pressure of something is the sum of all the partial pressures of the different gases in the mixture. So when we said that atmospheric pressure had a pressure of 760 millimeters of mercury, that's the sum of all the gases that, all the partial pressures of gases that are present in our atmosphere. In addition to that, it's also stating, Dalton's law, that the pressure exerted by each gas is directly proportional to that percent of gas in the mixture. So, for example, we have four gases in our atmosphere, and they're all present in varying amounts. So, the predominant gas in the atmosphere is nitrogen, and then we have 20% carbon dioxide, and we have very, very, very little, I'm sorry, oxygen. And then we have very, very, very little carbon dioxide and water down here. So how did we find all of these different partial pressures? Well, we used Dalton's law. We know there's 760 millimeters of mercury total pressure from all of these gases. So we basically take the percent of that gas found in the atmosphere. So if we change this to a percent, we would get 0.786 and times it by total atmospheric pressure. And we would find that the partial pressure due to nitrogen is 596. And again, if we did the same thing for oxygen, if we took 20.9 basically percent of 760 millimeters of mercury, we would find that oxygen's contribution to the total pressure is 159. Same thing with carbon dioxide. If we took 0.04% of the total 760 millimeters of mercury, and we would find out that the partial pressure attributed by carbon dioxide is really only 0.3 millimeters of mercury. And we do the same thing for water. And then we add up or sum all of these all of these partial pressures, and we find that they would add to atmospheric pressure. So that's basically what Dalton's law is saying, is that this total pressure is the sum of all these different partial pressures, and that the pressure exerted by each gas, so each one of these numbers is found by how much of that gas is in the atmosphere or in whatever mixture we're talking about. So again, whatever percentage is there. So we had 78.6%, and that's its partial pressure. Um, Henry's law talks a little bit about the solubility of a gas in a liquid, and there's a couple of different things incorporated into Henry's law. One is partial pressure when we're talking about solubility. So, in regards to partial pressure, each gas is going to dissolve into a liquid in proportion to its partial pressure. So, basically, um, I'll write that. Okay, solubility, it kind of varies. It's not something that's concrete. I wouldn't expect you to know a whole lot about the solubilities other than that of carbon dioxide and oxygen. Um, so it's variable, and the only thing I really want you to know about carbon dioxide and oxygen is that carbon dioxide is about 20 times more soluble in water than oxygen. And then temperature. So, in regards to temperature and gas solubility into a liquid, If we increase the temperature of something, of the liquid, we are actually going to decrease the gas's solubility. We decrease its solubility because we've increased with temperature the kinetic energy of the gas molecules, meaning they're going to want to bounce around and exit the liquid more quickly. So, those are the three components when we talk about gas solubility in a liquid. And both the partial pressures, when we talked about Dalton, as well as solubility in a liquid, Henry's law, is going to come into play when we talk about external respiration and internal respiration. So external respiration, again, this is going to be gas exchange between our lungs and our blood. Um, how do we influence how much gas is exchanged and in which direction between our lungs and our blood? It's going to be dependent on three different things. So partial pressure gradients and gas solubilities, that's what we just talked about with those two laws. If we look over here, I already wrote them out for you. You do not need to know these exact numbers that I have written here. Just understand which one's higher in which of these components, and in which direction it's going to flow based on which one's higher or which one's lower. So when we're talking about external respiration, we've moved on basically to the second phase. So we have inspired air. Our alveoli have a ton of oxygen in it. So in our lungs, we're going to have a really high partial pressure of oxygen, about 104 millimeters per mercury. Carbon dioxide is going to be lower than oxygen in our lungs. And when we talk about our blood, because this is the blood that's coming back to our lungs after it's dropped off the oxygen and picked up carbon dioxide, we're going to have lower oxygen levels because we've delivered it to tissues, and slightly higher carbon dioxide because we've picked it up from the tissues. So when we're talking about external respiration, lungs have the highest oxygen, and blood has the highest carbon dioxide. So now, again, we can go and apply the two laws that we were just talking about and figure out in which direction these gases are going to naturally flow. And that's going to be from a higher pressure gradient of the gas to the lower pressure. So if we're looking at the lungs and focusing on oxygen, we're going to have oxygen flow. Let me change it. From our lungs into our blood. Now, if we're looking at carbon dioxide, which I thought I got the right color, but I guess I didn't, our partial pressure of carbon dioxide is higher in our blood than in our lungs. So carbon dioxide is going to flow from our blood to our lungs during external respiration. The difference in the pressures of carbon dioxide are a lot smaller if you look at compared to that of oxygen. It doesn't matter. As long as it has a higher pressure gradient in the blood compared to the lungs, we're still going to get the same flow that we want for carbon dioxide. The second thing that can influence gas exchange between our blood and our lungs is the thickness and surface area of the membrane. So in order to increase our gas exchange, we would want to have a really thin, the thinner, the quicker, and a membrane with a large surface area. So if we have anything that's going to cause our membrane to be thicker, so something like inflammation, that would decrease our ability to do gas exchange in external respiration. Surface area, for the most part, is pretty much consistent unless we do something with our surfactant, and we don't have surfactant, and it's going to reduce the surface area of our alveoli. The third thing, and probably to you the most complicated thing that can affect gas exchange between the lungs and the blood, is ventilation-perfusion coupling. So the whole goal, and I wrote that down here, of ventilation-perfusion coupling is to actually match them, because we want to match ventilation, which is the actual gas that's reaching the alveoli, to the blood flow, which is perfusion. So this is blood flow in our pulmonary capillaries. Okay, when we're talking about ventilation or the amount of gas that's able to reach our alveoli, the partial pressure of carbon dioxide is going to play the largest role in this because it can change, that triangle means change, bronchial diameter. So if we increase the amount of carbon dioxide in our alveoli, we're going to dilate our bronchioles. And if we decrease the amount of carbon dioxide in our alveoli, we're going to constrict them. We're talking about perfusion or blood flow in our pulmonary capillaries. The partial pressure of oxygen is going to be key here because it can change the arterial diameter. So if we increase the oxygen in our alveoli, we're going to dilate our capillaries. And if we decrease the oxygen in our alveoli, we're going to constrict them. Okay, so let's, now that we have this information, do a couple examples or talk through two situations in which we would need to alter either perfusion or ventilation in order to match them together. So let's talk about a scenario in which our ventilation is less than our perfusion. This meaning that we have low oxygen, say, or low oxygen in our alveoli. And that would mean that our perfusion or our blood flow would be much higher. So we don't want this because if we have our perfusion and our ventilation mismatch, we either cannot pick up enough oxygen or we cannot drop off enough carbon dioxide or something like that. So in this case, if we have low oxygen in our alveoli and our blood is flowing faster than it should be compared to how much oxygen we have, um, as the blood's flowing by, it's not going to be able to pick up enough oxygen because we have a low amount in the alveoli. So we want to slow our blood flow. So our response is going to be to low oxygen in our alveoli would be to slow our blood flow because we have a small amount of oxygen available for it to pick up. So in order to slow our blood flow, we would have to constrict our pulmonary arteries, and in addition, because we have low oxygen levels in our alveoli, our partial pressure of carbon dioxide is going to act to dilate our bronchioles. So we can increase the amount of oxygen reaching our alveoli. The opposite situation, in which we have a high amount of oxygen in our alveoli and a slower blood flow, we're not going to be able to adequately do our gas exchange based off of partial pressure differences. So our response would be the opposite of the other situation. So we would want to increase our blood flow in order to match it to the amount of oxygen present in our alveoli. So in order to increase our blood flow, we would have to dilate our pulmonary arteries. And because we have a huge amount of oxygen in our alveoli, we want to try to again match it to our perfusion. So we would want to constrict our bronchioles as well. So again, this is the overview of the two laws. We talked about Dalton's law of partial pressure and Henry's law regarding gas solubility and how those apply to external respiration, and then the three things that can influence gas exchange between our lungs and our blood. And we'll move on to internal respiration in the next